Hello, this is how to train a quantum neural network. My name is Larry Leibovich, and I'm an adjunct research scholar at Columbia University in New York City. Traditional computers have variables, which are either integers or continuous values, and each variable has one value. There are also Boolean operations on those variables, like not or, but each operation does one thing to those variables. And there are arithmetic operations like addition and division, and more complex ones too. And each operation does one thing. This system lives in a space that has dimensions 2 times n, if n is the number of bits. But quantum computers are very different from this. Their variables have multiple discrete values at the same time. That's quantum mechanics, and it's called superposition. But when we measure one variable, we only find one of those values. There are two different types of quantum computers, one of which uses quantum gates, where each operation of those gates does many things to each qubit. And we can have a program that uses those gates to solve the problem we're interested in. Different kind of quantum computer is called a quantum annealer. And what it does, it computes the energy using the quantum rules between the qubits to determine what the energy of the system is. Here, finding the energy minima is used to solve the problem. These quantum computers live in a dimensional system of 2 raised to the n dimensions, which is a lot larger than the 2 times n for the traditional computer. And that's one of the ways they generate more power. In fact, quantum computers can break some codes 10 to the power 28 times faster than traditional computers. So for traditional computers, we know how to train them to solve problems, especially using neural networks and deep learning. But for quantum computers, we're just now creating ways to train them to solve problems, especially using neural networks and deep learning. This video is about how to train a Hopfield Ising neural network on a quantum annealing computer. So here we have a traditional neural network. It's designed like the brain's visual cortex, which is back on the top of your head toward the back. You can't see it now, but I'm holding my palm of my hand on my head above where the visual cortex is. And there are nodes of the network which are like nerve cells, and links between them, which are like the synapses between the nerve cells in the brain, of how information is carried from one node to the other, or one neuron to the other. And it has many layers, which are feed forward, meaning we start at the input and we go through maybe many intermediate layers and wind out at the output. So how does this work? Well, each node has a value, and the output from one node to another node is the value of that input node times a weight factor. In large language models, these weights are called parameters. And the input into a given node means the sum of all those inputs changed by a function, which is called an activation function. And there are several different nonlinear algebraic activation functions. This system will have many layers, and the information travels from the input nodes to the output nodes. So how do we train these systems? Well, we don't do it the way traditional programming has always done things, which is you write code where you know specifically what you want it to do. Instead, what we do, we're going to give it examples where it has known inputs and we want it to produce some known outputs. And then what the system is going to do, it's going to learn from those examples how to adjust its own weights so that what we want to get out of it is that we'll get the correct output for each input. And more than that, it will generalize to give good outputs to inputs it's never seen before. And the algorithm to do this, to adjust the weights, is called backpropagation. So what we do, we fix the input. We know what output we want to get from the system, and we first do a forward pass from the input to the output. And at the end, though, the output we get doesn't match what the output we wanted. So what we do is from that difference, we now do a backward pass that changes what's needed in the weights until the output matches the output we want. This algorithm is explicit. We can write down all the equations for it. So it's also analytic, and it's usually done with matrices. And this is an example of that. This is the MNIST set of digits. These were handwritten digits by workers who worked the 1990 census and high school students in Bethesda, Maryland. Each digit has been recorded on a 28 by 28 set of pixels, and each pixel has a grayscale of 256 values. And for example, this is the number 8. We can train a neural network to recognize these numbers. So we start with this 2D array of 28 by 28 pixels, and then we flatten it to a 1D array of 784 pixels. And then that will be the input into the neural network, those 784 different inputs, each one representing the value of one pixel. Now, it's not usually said, but I want to be very clear what is really happening here. What we're doing is we're taking horizontal slices, 28 of them, through this picture and then connecting them end to end. That's this one-dimensional array. So the neural network doesn't see anything like this 8 the way we see it. It sees all these separate 28 slices through it, all disconnected from each other. Even though it's somehow able to find patterns in those values of those individual pixels to be able to figure out that this is the number 8. This particular neural network, it has 128 nodes in the hidden layer that is in between the input and the output. And at the end, there are 10 output nodes from 0 through 9. And the value that is largest in one of these output nodes will tell the neural network, or how the neural network will report what the digit is. And it will use this algorithm of backpropagation. Typical application would be to train on 60,000 digit images and test on another 10,000. And so here, as the training steps increases, you can see the accuracy increases, and overall, the test accuracy of the digits, it's 97% accurate in figuring out which digit that was handwritten corresponds to which digit 0 through 9. Well, now let's look at what a Hopfield Ising network looks like. The design here is that it is a fully connected unit. The nodes only have discrete values. That's quantum mechanics. The links from one node lead to all the other nodes. So each node is connected to every other node. And there's a way of computing the sum of the energy of all these binary interactions using quantum mechanics. So there's no layers. So what we do is we want to pick some nodes as input and some nodes as output. So how does this work? What we're going to do is fix the values of the input nodes. Then we're going to find an energy minimum, and then we'll be able to read the values of the output nodes. And here's an example of commercially available quantum annealers that can do that. This is the DW2000 from D-Wave Systems. Here, the nodes, or the qubits, are little electrical oscillators that are built into integrated circuit chips. And this is the QCI Direct 3 made by Quantum Computing Inc. And here the nodes or the qubits are photons or little pieces of light. So in a traditional neural network, the node values are usually continuous, but in the quantum network, they're discrete. There may be integers, or they may be the angles of a vector in each node pointing in only a limited number of directions. The connections between the nodes in a traditional neural network are algebraic nonlinear activation functions. In the quantum neural network, they're the quantum rules of how the values in adjacent nodes contribute to the total energy of the whole network. The topology of the traditional neural network is feed forward. We compute from input to the output. The quantum neural network is fully connected. Each node is connected directly to all the other nodes, and we compute everything, everywhere, all at once. The forward pass for the traditional neural network, we compute from the input to the output. In the quantum neural network, everything is connected. So what we're doing before we do any training, we're looking at the initial state of it and finding the energy minimum. Then the backward pass in the traditional neural network, we know the output we want. We uh, run from we've already run to the output. So we compare the output we got to the output we want. And now we propagate backwards the changes in the weights until the output equals the output we want. In the quantum network, we can't fix the output we want. Everything is fully connected and everything is running all the time. So we can't just hold it there and work things backwards. So back propagation won't work. So what we need is something different. And this is what we need. So again, similar to the traditional network and the quantum network, we are going to give the system known inputs and known outputs. What we want is that we want the system to produce correct outputs for each known input. And we also want it to generalize, to give us good outputs to inputs it's never seen before. Here, the algorithm to do that is called equilibrium propagation. So the way this works is we fix the input. We do that forward pass, which will determine the first energy minimum before any training. Next, we weakly hold the output near where we want it to be. And we do a backward pass to nudge the system into a new state where its output will be closer to the output we want. But we can't move it too far because everything will interact and we'll just knock the network off where we are. So we nudge it a little bit, calculate the new energy minimum, and then repeat this process multiple times. So this algorithm is implicit and numerical. We don't explicitly write down in a single analytic form all the changes we want. We need to implicitly determine and numerically the energy minimum and implicitly determine how we're changing things. And this is an example of such a network being trained to recognize the MNIST digits. So in this quantum neural network, there were 5,000 qubits that were either zeros or one. The network was fully connected. It's a little more complicated than this because this particular machine has the qubits arranged in sets of 4 by 4. And so you need additional connections in order to logically connect everything globally, but that could be done. We have to combine several of the qubits to create enough information to separately represent the digits 0 through 9. And the algorithm here is equilibrium propagation. So we're going to train this network on 1,000 pictures of digits and test it on 100. And here as the number of training images increases, you can see the accuracy and the test accuracy over here of the actual quantum computer is about 89% accurate. What they've also done here is do a computer simulation of what would happen if this quantum computer had a lot more qubits. And if that were the case and they were able to analyze 10,000 images, actually the accuracy that you would get of that computer is actually close to 97%, which is very close to what the traditional neural network got. So, to summarize, a traditional neural network, we train it using backpropagation. So we fix the input, we know the output we want, we do a forward pass and compute from the input to the output, but we didn't get exactly the output we want, but we know the difference. And then we can propagate that difference backward to produce the needed change in the weights to get the output we want. This algorithm is explicit and analytic, usually using matrices. This whole system has relatively low complexity. That is, it has a dimension of 2 times n, where n is the number of bits. This contrasts with the quantum Hopfield Ising network run on a quantum annealing computer. Here, the training algorithm is equilibrium propagation. We have a fixed input. We do a forward pass to determine the energy minimum before any training. We then weakly hold the output near the output we want and do a backward pass to nudge the output and therefore the whole system, since everything is connected to everything else, to a new state. And we can only do this nudge since everything is inside is active all the time. And once we've done that, then we find the new energy minimum and repeat this process. So this algorithm is implicit and it's numerical. And this whole system for a quantum computer lives in a much higher dimensional state, 2 raised to the n for n qubits. And this is some of the powers of the quantum computer come from, is having a much higher dimensional system, which gives it more power to do and solve problems. And here are some references describing what I've covered, some references on traditional neural networks, training these quantum Hopfield networks in Ising models, and some use cases for them. For example, many problems called non-polynomial or NP problems, which are too difficult, that is, they would take too much time and too much memory to solve on traditional computers, can be solved by Ising formulations, and in principle could be solved this way on quantum computers. Thank you.